Hi, everybody. I'm Marvin. I'll be talking about charting the space of ground states with MPS. Thanks for the organizers for giving me this opportunity to talk. And yeah, let me begin by acknowledging my collaborators. So David and Shweta are UQM postdocs. Daniel, Marcus, and Agnes are mathematicians at CU Boulder, and Mike obviously needs no introduction. So let me just get started. So I'll start with a brief introduction and just to set the stage, and I'll include some motivation on why we should care about this topic. I'll briefly talk about parameterized systems, the definition, and some familiar examples. And finally, I want to get to this example of the chern number pump and how we use matrix product states to better understand and get a different perspective on it. So that out of the way. So just to set the stage, everyone here is familiar, but as condensed matter physicists, we're interested in understanding quantum phases of matter. And the context here is that we have some lattice model. There's some on-site Hilbert space associated to each site in the lattice. And our Hilbert space is an infinite tensor product. Our Hamiltonian will be the sum of local terms. And we're interested in the ground state of such a Hamiltonian. And in particular, we'll be interested in the situation where in the thermodynamic limit, there's a finite energy gap between the ground state and the first excited state. So so the context that we'll be focusing on are gapped quantum lattice models. And one reason that these are particularly interesting is that there's a natural way of partitioning these quantum lattice models into equivalence classes. And these equivalence classes are what we typically call phases of matter. And when are two lattice models in the same equivalence class? Well, we say that two systems are in the same phase if they can be deformed into one another while preserving the gap. So that's how we partition their system into equivalence classes. And the reason that we care about the reason why this is useful is that systems that are in the same phase, they have the same universal properties. And this could be taken, as a definition of what a universal property is, it's just something that stays the same within each phase. But these are things that typically we're interested in, such as braiding statistics or the presence of edge modes and stuff like that. So understanding quantum phases of matter is like trying to understand what are the phases and what are the universal properties. So one question that we always have, this might be like the starting question, is to try to classify these phases of matter. And let me try to frame this classification question as a topological problem. So here I've just drawn a schematic for the space of all possible quantum systems, maybe all possible ground states of quantum lattice models. And let me begin by just throwing out all of the systems that are where the gap closes. So these are systems that have zero gap. And now let me label this special point in this space of states. This is the trivial product state. And once I've thrown away these gapless points, it's sort of clear now that there are systems that I can't reach from the trivial product state by adiabatic deformation while keeping the gap open. And so we would label these phases as being different. So we can assign some labels to this. This one is the trivial phase because it contains the trivial product state, but we might also have some spontaneous symmetry breaking or topological order or SPT or what have you. So these are just labels that label the different phases. But the main kind of takeaway that I want to leave you with on this slide is just that when we're classifying gapped phases, what we're doing is we're looking at this enormous space of ground states or space of quantum systems, and we're trying to understand, what are its connected components. So sort of with this framing, so what we're doing when we're classifying gap phases, we're trying to understand what's the pi zero, the connected components of the space of of gapped quantum systems. And with this kind of framing, it's relatively natural to ask, well, what about higher homotopy groups of each phase? Maybe this also gives us some useful information about the systems that we want to study. And at first glance, it might seem like this is kind of a bit of an academic question, like why should we bother caring about these higher homotopy groups? So to address that, let me draw an analogy with the study of defects and textures in ordered phases. So I'm imagining we're in just the ordinary Landau paradigm where we have some global symmetry G in our system. And this global symmetry gets broken down to some subgroup. And the subgroup, some subgroup H as a. Then we can label the possible ground states with by the cosets G mod H. So the G mod H labels the possible ground states. And the homotopy groups of this coset space will determine what kinds of defects and textures are available in the system. So for example, the pi k will determine what codimension k+1 defects there are and what kind of codimension k textures there are. So as an example, if we start off with Z2, the pi 0 will label what kind of domain walls we have. If we start off with U1 and we spontaneously break down to the trivial subgroup, of course, we're very familiar with the fact that you can have vortices in a two-dimensional system, and this is a codimension 2 defect corresponding to pi 1. And finally, if we have an isotropic magnet with SO3 symmetry, we could spontaneously break that to rotations about a single axis. So the coset space is this SO3 mod SO2, which is just the 2 sphere, and pi 2 of that will tell us, for example, what kinds of textures we can have in a two-dimensional system. So how this relates to the homotopy groups of quantum systems, if we have a non-trivial pi k in the space of quantum systems, one can imagine that this can lead to possibly interesting defects and textures. So one might imagine that maybe attached to this domain wall there's some chiral thing going on, or attached to this vortex maybe there's like a projective representation that's attached to the core, something like that. Cool. So let me move on to introducing the notion of parameterized systems. So parameterized system is basically a way to try to probe the topology or the higher homotopy groups, or more generally the topology of the space of gapped Hamiltonians. So we say a system over X is just a map from X being a topological space to the space of gapped Hamiltonians. And we should think of X as being kind of like the set of parameters, a parameter space, which encapsulates like what kind of parameters hypothetical experimentalists could tune. So it could be something like the magnetic field or the strength of certain couplings or anything like that. And just by analogy to the ordinary classification of phases case, we would want to say that two systems over X, H1 and H2, are in the same phase over X if they can be deformed into one another while preserving the gap everywhere over X. So H1 and H2 you can think of as just some family of gapped Hamiltonians, and if I can deform one to the other, we'll say they're in the same phase over X. And to say anything about what's trivial or non-trivial, we want to say we want to define the trivial phase. So a system over X, we'll call it trivial if it's both constant as a function of X and the ground state is a product state everywhere. And both conditions will turn out to be important. Okay, so to establish some base cases, let me just remind the audience of how this relates to what we're already familiar with. So if X is taken to be a point, this just reduces to the ordinary classification of phases. And moreover, if X is S1, sort of the simplest non-trivial X, this describes what are typically known as quantum pumps. So for example, the famous one is the Thales charge pump, but you could also imagine pumps of SPTs, or maybe there's a nowadays people are thinking about these kinds of EM duality exchange pumps. So these are the kind of two most familiar contexts in which people typically think about parameterized systems. But I just want to, for this talk, I will want to focus on an even simpler system, which everyone is familiar with, and that's the famous Berry phase example in 0 dimensions. So here we take our parameter space to be the 2-sphere S2. So for each point in S2, this W is a norm 1 vector, and it determines a Hamiltonian, which is given by W dot sigma. So this Hamiltonian is gapped, and therefore it defines a parameterized system. And the claim is that this parameterized system is non-trivial. Of course, we're familiar about why that is. There's a phase invariant that you can attach, that you can associate with this system. It's given by the chern number. And this chern number takes on a quantized value. So it's going to be multiples of 2 pi. And the way that one can compute this is that you take the Berry curvature, which is a 2 form, and then you integrate it over the parameter space S2, and you obtain 2 pi. So what this quantized phase invariant tells us is that it's impossible to deform the system into a constant family over S2. An example of a constant family would just be, where I plug in some value of W, some W vector, and my Hamiltonian is just sigma Z. So it just doesn't even depend on W. And the reason that it's impossible to deform this system to this constant family is because that the chern number associated to the constant family is 0, whereas the chern number associated to the spin half in a magnetic field is non-zero, and so it's impossible to go between them smoothly. So that's the simplest example of a non-trivial parameterized system. And let me examine a notable consequence of this. So let's try to write down the ground state wave function of this family of Hamiltonians. So on the northern hemisphere, I'm imagining this the northern hemisphere kind of extends down past the equator. You can write down the ground state wave function. It's something like this. And notably, it's actually, you can't, this wave function is not well defined at the southern hemisphere. So you can't extend it all the way down. At least that's what it looks like. And similarly, you can write down a ground state wave function on the southern hemisphere, and you find that, okay, you actually can't extend it all the way up to the North Pole. And these two wave functions, they represent the same state, so they must differ by phase. And the phase that they differ by is this e to the I phi. And what's notable about this e to the I phi is that, so this, on the double overlap where both of these wave functions are defined, the wave functions are related by this phase e to the I phi. And this e to the I phi has a non-trivial winding number around the equator. So what this tells us is that this is an obstruction to finding a globally well-defined wave function. And the reason is that if I did have a globally well-defined wave function, the transition function, you could take it to be trivial, and that would have no winding number. And that's, you can't go between winding number 0 and winding number 1 continuously. And this is just another way of saying that the chern number is 2 pi. Okay, so that was the simplest example of a parameterized system. Now let me move on to, and that was in 0 dimensions. So let me move on to this chern number pump, which is a 1-dimensional system, and talk about how we can use matrix product states to analyze this. So the one-dimensional example that I want to talk about will have a non-trivial higher Berry phase, and this higher Berry phase was introduced by Kapusta and Spodenko. And this lattice model that I want to talk about, this is defined. This is a family over S3. And we parameterize S3 with a 3-vector W, just as before, and then a fourth scalar with W4. And these 4 numbers are constrained to their sum squares to 1. So that's how we know we're living on S3. So to define this model, I'll define the Hamiltonian on various patches of S3, which I've drawn here. and W4 goes vertically. So within this kind of central patch, so this is the region W4 between -0.5 and 0.5. We just take the Hamiltonian to be a bunch of decoupled spins in a magnetic field. So each unit cell has 2 spins, and the spin points in opposite directions for each spin in the unit cell. So this Hamiltonian is completely decoupled. It's a product state, and it depends on this W vector. Now, for the lower hemisphere, what I want to do is add a Heisenberg antiferromagnetic exchange interaction. And what you can notice is that, so I have this still spin in a magnetic field term, and I also have this Heisenberg exchange term. But as I take W4 to -1, the W vector goes to 0 because I'm constrained to live on the 3 sphere. And so what's happening is I'm slowly turning off this magnetic field and increasing the strength of this Heisenberg interaction. And at the actual pole, the magnetic field disappears. The Heisenberg interaction is the only term in the Hamiltonian, and we get spin singlets on each unit cell. Now, similarly, on the upper hemisphere, I want to do the exact same thing, but this time introduce the Heisenberg interaction on inter-site bonds. So once again, the magnetic field is slowly being tuned to 0, but the Heisenberg interaction is being slowly turned on, but now the spin singlets sort of live on inter-site bonds. So that's the definition of the model. You can see that model is sort of trivial in the sense that there's only ever 2 spins interacting with each other at a time. So actually, this model is really a sum of decoupled 0-dimensional models. So that's what makes it possible to solve. So
function G plus and G minus.
Oh yeah, the function. So yeah, the function G plus and G minus, you can take it to be it's just turning on W4 linearly when so yeah, you can just think of this as W4 and this one as minus W4.
And it vanishes and when it's a half, when W4 is a half, such that it's continuous.
Yeah, exactly. So it turns on here and it interpolates between 0 and 1. And similarly here, it turns on and interpolates between 0 and 1. Exactly. Yeah, thanks. Okay, so this kind of construction is very reminiscent of these quantum pumps. So that's why we'll call it a chern number pump. It's a non-trivial 1D system over S3. And there's 2 different ways to see this. The first is that you can calculate the higher Berry curvature, which is introduced by Kusin-Spodeniko. You can calculate the higher Berry curvature and integrate it over S3, and this takes on a value 2 pi. And the other way to see it is that if you look at the boundary, let's focus on this left boundary. So everywhere, or almost everywhere, this left boundary is just gapped. It's kind of trivial. But you'll notice at the actual pole where the magnetic field turns off, this spin can't pair with any neighbor. And so this spin will be gapless at a single point. So the 0D boundary will have a single vowel point over S3. And that's impossible to have just for an isolated 0-dimensional system. So there's some kind of boundary anomaly associated to parameter space here. Okay. So this chern number pump is a 1-dimensional system, and matrix product states are sort of a very natural tool to use to analyze 1-dimensional systems. And so we can represent the ground state of this chern number pump using an MPS ansatz. These A's are essentially 3 index tensors. The I is the sort of physical index, and there's alpha and beta, which are the bond indices. So the MPS tensor can be represented schematically, something like this. And the bond dimension is roughly quantifies how much entanglement is present in between the different sites. So in particular, if the system is not entangled, if the bond dimension is 1, then the sites are sort of not entangled with each other. So let me just go ahead and illustrate what the MPS representation for this chern number pump is. On the northern hemisphere, we see that there's some entanglement between the two sites, the two neighboring sites. So what we need is a bond dimension 2 matrix product state. So the actual form of this is not important. I just want to point out that for, if you plug in values for I and j, this spits out a 2x2 matrix. And this description is valid sort of in this region W4 greater than -1/2. So it includes the equator. And similarly, you can do the same thing for the lower hemisphere. This time I'm taking the lower hemisphere to be W4 less than +1/2. So again, it includes the equator. And here you can see that there's no entanglement in between the different sites. And so the bond dimension is actually, it's actually just 1. And you can see if I plug in values of I and j, this just spits out a number. Okay, so just like in the 0-dimensional story, we can compare the different MPS representations as opposed to the actual wave functions. We can compare the MPS representations on the double overlap, which is the sort of equator of the S3, which is like S2. So it turns out that because they represent, of course, on the equator, these two MPS representations, they represent the same state. So they're related by this pair of matrices V and W. So this pair of matrices is called a reduction. It satisfies VW as the identity. And one thing I want to point out is that these matrices V and W, they're actually only well-defined up to a phase. So I could redefine W by e to the I phi and V by the opposite. And this combination remains unchanged. So we could go ahead and calculate what this V and W is for the system. If I choose, so remember W is only well-defined up to a phase, but if I try to pick a representative, I get something like this. And you'll notice that this pesky e to the I phi means that it's actually not well-defined over the entire 2-sphere. And actually, it turns out that this phase ambiguity for W, the fact that you can't define it over the entire 2-sphere, it's the exact same phase ambiguity of the ground state wave function for the spin-half and magnetic field that we saw earlier. So what we can say is this W carries chern number. And what we would say, so this reduction, this pair of matrices V and W has a non-zero chern number. And just like before, where the non-zero winding number implied a obstruction to finding a global wave function, this non-zero chern number represents an obstruction to choosing a globally well-defined MPS for the system. I think I'm running out of time, so let me just skim over what the general structure should be. The collection of MPS representations for a ground state, together with all the kinds of transition data, this assembles into a data for a gerb. And a gerb is just a kind of higher dimensional generalization of a line bundle. And hopefully the analogy to a line bundle will be clear. So essentially, given a suitable open cover for our parameter space, we can assign a bunch of MPS tensors, which represent the ground state for each open set. And moreover, we can associate line bundles on these double overlaps, which relate the MPS tensors A and B. So before, for the 0-dimensional case, we had transition functions. That was the e to the I phi. And now we have these transition line bundles. And furthermore, this is something that I didn't talk about, but it turns out you also have to associate these kinds of isomorphisms, which tell you kind of how to compose the different transitions. And these isomorphisms will satisfy a co-cycle condition. This gerb, this data that I described in the previous slide, you can associate to it an invariant, which is similar to it's analogous to the chern number. It's called the Dixmuir-Doherty class. And this lives in the third cohomology, just like the chern number lived in the second cohomology. And this class, you can also, this is precisely, what the integral of the higher Berry curvature measures. And so, so what we've shown basically is that if you have a non-trivial higher Berry curvature invariant, there's also an obstruction to a global MPS representation. So just to summarize, so MPS provide a powerful framework for analyzing these 1D parameterized systems. For the chern number pump, you can see the non-triviality by looking at the chern number of the transition line bundle. And more generally, you can extract a gerb structure associated to MPS representations of parameterized families of 1D states. So some further directions along this line is, we have this gerb, we can try to define the gerb connection and maybe even recover the higher Berry curvature invariant. And another possibility is try to directly analyze this classifying space of matrix product states. So these are sort of work in progress. And of course, I have to mention this set of parallel works by Shuhei Oyama and Ken Shiozaki and some other and their collaborators. In particular, this second paper offers a really nice perspective on how to obtain the gerb for a family of matrix product states. So they analyzed the same question and with a different perspective, and they came across they got a really nice result. So that's all for me. Thanks for listening.
Great, thanks, Marvin, for the very clear and nice talk. Are there questions from the audience? You can just unmute yourself. So I do have one quick question. So it looks like the gerb is dealing with the H3 obstructions. Can you do H4 or even higher using NPS?
So it's certainly it's expected, this kind of thing is expected to continue on to higher dimensions.
Mm-hmm.
There's just some technical difficulties. Part of what allows us to sort of be rigorous is the fact that there are these theorems, these structure theorems for matrix product states in one dimension. In higher dimensions, it's difficult. For a specific model, which is the 2D version of this chern number pump, we can sort of write down the same story. But I think this general higher gerb structure is pretty difficult to extract.
I see. Okay, thank you.
But let me just say, in the 2D case for this chern number pump, it's sort of the same story where on the double overlap, basically you have the transition thing is a family of 1D states. So the transition thing is a 1D gerb, which is precisely the 1D chern number pump. So that's how that example extends to 2D.
I see. Thank you. Any other questions?
Yeah, I have a question. So this chern number and other things, like it does some kind of z-valued topological invariance.
Yeah.
Whether this, I imagine those gerb probably also can have some kind of zn value, like z2 value, the z3 value invariance. Yeah.
Yeah, good. So one thing I didn't mention, maybe here. So in this chern number pump example, the MPS on the upper hemisphere and the MPS on the lower hemisphere have different bond dimension. And so that turns out to be essential to capture the Z invariance. You could also imagine a different parameterized family, which where the bond dimension everywhere is the same. And in that case, these V and Ws are essentially like gauge transformations for the matrix product state. And in that case, those kinds of situations would capture torsion invariance in the H3.
I see.
So if for example, if you want to sort of restrict to constant bond dimension matrix product states, in fact, you will only see the torsion.
I see. Okay.
Yeah. So in our paper, we have an example, and also in those set of papers by Shuhei, they also write down essentially, yeah, the same example, same universality class.
Thank you very much.
Any other questions? Okay, if not, let's thank the speaker again for now. And if there are more questions, we can do it during the free discussion time. So let me stop the sharing for a moment. Stop the recording for a moment, and